wanting to put students in a position to succeed, I continue to work out problems from the problem sets, problems in which there will be other problems on the exams that are just like these problems that I'm working out. So this first problem I'm going to work on is labeled number 2 in problem set 5. And more specifically, we have I'm going to draw a circle. And at some point on that circle, like say a point right here, you have a car that's going around a curve. And so let's zoom in. Let's say that we're focused on this semicircle right here, and the car is going around that part of the circle. When you have circular motion, you can define an axis of rotation, and then there's going to be some distance from the axis of rotation to the circumference of the circular motion. And so we are going to call that orange R. R is going to be the distance from the center of the circular trajectory to the location of the mass that is going about the circular trajectory. So if I was to blow that up, you can imagine there would be some R. And it turns out that when you have uniform circular motion, you need to have a centripetal force that provides that uniform circular motion. At any moment, when you have circular motion, your velocity is actually tangent to the circle. So if all of a sudden the force that's keeping you in the circle just went away, then the red dot you see right here, which represents the car, that would just keep following the green line. It wouldn't just stay in a circle on its own. It has to have some force that is keeping it in the circular motion. And so we define a centripetal force, which I will call FCEN, as equal to the mass of the object doing the circular motion, the velocity of the circular motion squared, divided by r, which is the distance from the center of the circular trajectory to where the object is located. And so just to point out, if I take out the mass m, v squared over r, that is my centripetal acceleration. I need a force that supplies a centripetal acceleration to keep the mass in uniform circular motion. If that force does not live up to mv squared over r, let's say it weakens so it doesn't supply mv squared over r anymore, you're not going to have motion at the same radius away, certainly not circular motion. So you need to have a magnitude that's mv squared over r, and you need to have a direction, and so this is where I'm going to draw in blue. That's the direction of the centripetal force. It has to be perpendicular to the circular trajectory, because at any moment in a circular trajectory, the velocity vector is going to be tangent to the circular trajectory. And so if you, for example, let's say, hypothetically say instead my centripetal force was like this right here, can you see how there's a component of that force that's in the direction of the green, which would make the green even bigger? And so you're not going to have the same circular motion at the same radius r away if the centripetal force is anything other than perpendicular. You need all of the centripetal force to be perpendicular to the direction of the velocity. Again, the direction of the velocity is perpendicular to the circular trajectory. And so the centripetal force points directly towards the center of the circular trajectory, and it has a magnitude that is equal to the mass times the velocity squared divided by r. There can be no component of the centripetal force that is in the direction of motion Or if that was the case, then the v, which is the speed, well, the v would increase, but we need the v to stay the same. This is a little counterintuitive because you're maintaining the same speed, yes, when you go through circular motion. But if you think about it, the direction is always changing if it's going about a circle. It's not going in a straight line ever. It's always changing. And indeed, you need to have the acceleration towards the center for that change to be such that the v stays the same when the direction changes. So, uniform circular motion, the v is the speed. The velocity is actually a vector that's tangent to the circle. To keep that vector from growing, you always have to have the centripetal force provide an acceleration that's perpendicular to it. And I show you mathematically that it's equal to mv squared over r. Okay, so now let's go back to our car and let's do a dynamics breakdown. In the vertical direction, there's going to be mg, which is the mass of the car and the gravity, and that's pulling down on the road. However, when the car gets pulled against the road pushes back on the car. This is an action-reaction pair, and we're going to call this the normal force. The normal force is supplied by the road. If we sum our forces in the y direction, we get a normal force minus mg equals may, which is acceleration in the y direction. By convention, we'll let positive x be to the right, positive y be up. That's why I have this negative sign here, because mg is down, Fn is up. And so since those are action-reaction pairs, they are equal and opposite, and so that means that they're equal to 0. In other words, there's no acceleration in the y direction. And so another way you can rewrite this is the normal force is equal to mg. Now, let's think about the direction horizontally, which I'm going to say the sum of the fx. And so horizontally, we actually, because in this problem we were told that there's not going to be any banking of the curve. It's going to be a completely flat curve. And so we're also told that ice is melted. And so that means that there's going to be friction between the tires of the car and the road. When it's ice, you have less friction. You'll have more slippage. But when the ice goes away and you have this pavement rubbing against the tires, it's going to cause friction. So if you can imagine the car, and again, the car is represented right here, if it comes whizzing around and all of a sudden, like, it didn't have any traction anymore, it would just keep going in the green direction. And so what keeps it in the circle is that you have a frictional force that is acting towards the center of the circular trajectory. This is the coefficient of kinetic friction multiplied by the normal force, which we call a cursive Fk, which is just the frictional force due to kinetic friction. And so this is equal to F of k, which is equal to the coefficient of kinetic friction multiplied by the normal force. We've already shown that the normal force is equal to mg, and so this is mu k mg. And this is equal, by Newton's second law, to the mass times acceleration in the x direction. And this acceleration in the x direction is precisely the centripetal acceleration. So it's the frictional force, the friction that comes from the tires rubbing against the pavement, that provides the requisite centripetal force to keep this car from slipping. And so we need to figure out what is mu k to keep this from slipping. So we can take our equations that we have in blue there, and we can rewrite them. More specifically, we can say if I have the mu k mg term and I want to isolate the mg, excuse me, if I want to isolate the mu k, so this term right here, if I divide both sides by mg, actually, I thought of an even easier way to do this. This mu k mg, right, which is the sum of the forces in the horizontal direction, which is the force due to kinetic friction. As I mentioned, so that's this force right here. This is the only force in the horizontal direction, meaning it is the only force that is supplying the requisite centripetal force, which is mb squared over r. The frictional force provides the centripetal force. I can't emphasize enough that a centripetal force isn't a thing by itself. It's a force that just happens to supply rotational motion. It could be, in this case, friction against the road. It could be, like, for instance, like if you were whirring around a ball attached to a rope, it's the tension in the rope that's supplying the centripetal force. So they're ordinary forces, they just happen to be oriented in ways that supply the requisite centripetal force. And so in this case, you have, this is the friction term supplying the requisite centripetal force. This can simplify because I have a mass right here and I have a mass right here. And so I can simply divide both sides by g, and I get the expression mu k equals v squared divided by gr. In this problem, we were told the mass of the car is 1,300 kilograms, and we are told the velocity going about the circular trajectory is equal to 65.0 kilometers per hour, and we are given the radius. The radius is 91.4 meters. So you can see we have the v, we have the r, and we know what g is. So one last thing, we are going to have to make a conversion because we know that v equals 65.0 kilometers per hour. We want to convert that to the SI meters per second. And so to make that conversion, just know that if we want to convert from kilometers to meters, well, 1,000 meters are in 1 kilometer. That cancels my kilometers. And then I need to convert from hours to seconds. Well, 1 hour is 60 minutes. 60 minutes is 60 seconds. 60 times 60 is 3,600 seconds. You see how hours cancel? And so all I would do to get v is just multiply all of the top and divide by all of the bottom. And so I have 65.0, 1,000, 1 divided by 1, 3,600. And that's how you would convert it into meters per second. And once you make that conversion, you put that term right here. And again, the radius term is this 91.4 meters. And so that's how you'd go about solving this problem. And again, I just want to reiterate, you can think of going around a curve as a little snapshot of going around in uniform circular motion. When you're going in uniform circular motion, you have to maintain the same velocity, but the key here is that the velocity is going to change every moment. So it's actually, you're maintaining the same speed. That's what the v is the speed, but the vector is actually tangent to the circle at any moment. So like if I had the car go right here, the magnitude would be the same, but the direction, you see how the direction, it's now tangent to the circle there. And so to keep it being tangent to the circle, you need to have a force that's perpendicular to it. But it's not like this thing called the centripetal force just shows up to do the job. Ordinary forces do the job. They just happen to be oriented in a way that provide the requisite centripetal force that's perpendicular to the uniform circular motion. In this particular problem, it was the rubbing of the car's tires against the pavement that provides a friction that is oriented perpendicular to the motion. And I showed you how you can formulate that friction as a coefficient of kinetic friction multiplied by the normal force. And because we summed our forces in y, we saw that the normal force is equal and opposite mg. So we can say that the force due to kinetic friction is mu k mg. And at that point, since we know that that is the force that's supplying the centripetal force, we can equate it to mv squared over r. And that's what allows us to go ahead and solve for mu k. The next problem I'm going to go over is what's labeled as number 6 in the homework. And this also is a problem where we can think of rotational motion. And so imagine we've got a string, and at the end of the string we have a stone, okay? And that stone has a mass, and the mass of the stone is equal to 0.800 kilograms. That stone is attached to a string. That string has some length L, and we are going to try to figure out when this string breaks if we swing around the stone at a faster and faster speed. So in other words, we want to try to solve for V max, which is the fastest we can whirl the stone around when attached to this string without the string breaking. Because what's going to happen is as we whirl this stone around faster and faster, if you remember, the centripetal force equals mv squared over r. Another way of thinking about it is force equals mass times acceleration. Well, centripetal acceleration is v squared over r, so mass times acceleration is mv squared over r. And so in this particular case, it's the tension of the string that provides the centripetal force. Because again, a centripetal force is not unto itself. There has to be some ordinary force that could or could not provide circular motion, and just so happens to be. And then we say that it's providing the centripetal force. And so it's the tension in the string. If you can imagine, like if this is the center of the axis of rotation, and if I'm whirling the stone around with this string, as the V gets bigger and bigger and bigger, well, on the other side of the equation, the tension needs to get bigger and bigger and bigger. In other words, you need more and more tension to be able to satisfy the stone continuing to stay in a circular trajectory at the velocity at which it's going about the circular trajectory. So at a certain point, if V gets so big, right, if this V right here gets so big, then this tension right here is going to get so big that the string's going to break, because the string can no longer support the tension necessary for such a high velocity of the stone whirring around. Okay, so again, this is another centripetal force problem, but now, unlike in the previous problem where it was the friction between the car and the road, now it's the tension in the string that is supplying the centripetal force. And so we're told in this problem that the T max that the string can hold up is 65.0 newtons. Okay, and so we are also told that the string has a length, and that length is 0.900 meters. So that's in meters, tensions in newtons, masses in kilograms, so we're good. We don't have to do any conversions. And so if you can think of just going around in a circle, the length of the string is precisely the radius r of the rotational motion. And so that is to say that our Tmax is equal to the mass of the stone Vmax squared over L. And we want to solve for Vmax. So what I'm going to do is I'm going to multiply both sides by L and divide both sides by M. So L Tmax divided by M is equal to Vmax squared. And so then if I take the square root of both sides, Vmax equals the square root of L Tmax over M. And we know L, we know Tmax, and we know the mass. So you can plug those numbers in and solve for the maximum velocity in which this stone can whir around in a circle. If it goes any faster than that, it would require a tension from the stream that could no longer hold up. The stream would break. And again, it's the stream that provides the centripetal force to keep this in motion. I keep talking about centripetal force. I highly recommend reading in the text about centripetal force, reading the text about rotational motion, and again, I also have videos where I go more into the conceptual understandings of centripetal rotation, centripetal force. I get into why the acceleration needs to be perpendicular to the motion, for example. So you've seen two problems from the fifth homework, which will also be problems exactly like you see on the exam. And so I want to do a third problem for you from this homework, which is labeled problem 8. And so in this problem, you can imagine that there's a pond of water and there's a limb of a tree, and we're going to say that the initial height of a person that's getting ready to jump off of this limb into the water, we're going to say that there's some initial height from the limb to the water. And so we are told that this initial height is equal to 3.90 meters above the water. We're also given the mass of the person about to jump in the water. The mass of the person about to jump into the water is 72.0 kilograms. So this is a problem where the only force that is acting on the jumper into the water, or the diver into the water, is gravity. And so if that person jumps off the limb right now, what it's going to allow gravity to do is to do work on the jumper. So here's this concept of work, which is tightly related to energy. So I highly recommend looking at other videos that get into the concepts of work and energy. So gravity, if the person jumps off the limb, is going to accelerate that person downward towards the water. Since that person's accelerating, it means their velocity is changing. Since their velocity is changing, it means their kinetic energy is changing. So you can think of gravitational potential energy as the potential for gravity to do work on an object. And when gravity gets to do work on an object, it changes its kinetic energy. And so you can think of problems where conservative forces, such as gravity, are the only forces that are acting. You can think of a situation where the energy before equals the energy after. And more specifically, you can think of the kinetic energy initial plus the potential energy initial is equal to the kinetic energy final plus the potential energy final. And so you can read in textbooks about how with gravity we can say that if gravity is doing work on an object, then we can define the kinetic energy as 1/2 mass times the initial velocity of the object squared plus, and so this is when gravity is the only conservative force that is acting. And again, check out my videos and I'll say more about what conservative means. So mgh is how we define gravitational potential energy. And so think of the left side of the equation as before, and think of the right side of the equation as after. So after, you have 1/2 mv final squared plus mgh final. So before, the sum of the kinetic and potential energy equals the sum of the kinetic and potential energy after, but their amounts might change. And so at the beginning of the problem, the person about to jump is not accelerating, and so all of their energy is potential energy right now. In other words, V naught equals 0. So that would mean that this term right here goes away. We're given the initial height. Now we can say that the height is above some reference point, and so it's easy to make one of the reference points 0, right? So if you can say that right now y equals HO, well, we could say that the water is y equals 0. So we can say that when they splash into the water, the H final equals 0. So this term goes away. So you can see here that when the beginning is the person on the limb of the tree and the end is them splashing into the water, then mgho, so it's all potential energy when they're just standing on the limb. There's no kinetic energy. Then if we define the water as a height of 0, at that moment we have all of our energy being kinetic energy because the height is 0, so there's no gravitational potential energy. So 1/2 mv final squared. And this v final is what this problem wants us to solve for. Both sides have masses, so we can get rid of the masses by dividing by m on both sides. And so v final squared is equal to 2 times gravity times whatever the initial height is. And so then v final is just taking the square root of both sides, and so it's just going to be 2gho. And we're in good shape here because we have g, of course, it's 9.8 meters per second squared, and we also have ho right there. So you would be able to solve for v final when it hits the water. So there's 2 more parts of this problem. One part of the problem is what happens if the person actually jumps straight up before they start falling back down to the water, and the other is what if they jump straight down into the water? What will their final velocity be then? So let me work out both of those for you. And again, we say that the kinetic and potential energy sum before equals the kinetic and potential energy sum after. So 1/2 mv initial squared, that's the kinetic energy initially, plus mgh, which is the initial height, is equal to 1/2 mv final squared plus mgh final. So every parameter is the same, with this. The difference is that originally I could say that the initial velocity v naught was 0, but now what they're doing is they're actually jumping straight up. And so when they jump straight up, we are told in this problem that the straight up jump is 2.10 meters per second. And we'll leave that as positive because it's up, and usually when we think of vertical y, we think of up as positive. Okay, so that term doesn't vanish anymore, but the initial height, That's exactly the same. If we go back and we look at our initial height, it's 3.90 meters. And we also can still say that the surface of the water is at height h equals 0. If the original height is h naught, we can say that the water is h equals 0. Another way of saying this is that y initial equals 3.90 meters and y final equals 0. So we can say that h final equals 0. So that's good because it means that this term vanishes. But now we've got 3 terms instead of 2 terms. And again, the name of the game is solving for what the velocity is when the diver splashes into the water, which is this term right here. So all 3 of these terms have masses. So if I divide it by mass, those terms go away. So then I have 1/2 v initial squared plus GHO is equal to 1/2 v final squared plus 0, because that term vanished because the height was 0. And we want to solve for v final squared. So what I'm going to do is I'm going to multiply both sides, each term by 2. If I multiply each term by 2, then 1/2 times 2 is 1, so you'd have a v naught squared. Multiply the 2g h naught by 2, and then your v final squared, 1/2 multiplied by 2 is 1. And so again, if I want to solve for v final, I gotta take a square root, so I can say that v final equals the square root of v initial squared plus 2g h naught. And we're good because we've got our v initial term right here, and we've got our h naught term here, and we know what gravity is. And check it out. The next part of the problem asks what happens if instead the velocity was a jump straight down, which would mean v naught would be negative 2.10 meters per second. It turns out that this term right here is a square, so whether the initial velocity jump up or down is positive or negative respectively, that term will be the same. But another way in which you can think about this, and I'll leave you with this, is that so if a person was to jump straight up off of the limb, they'd have some initial velocity, and when they jump, gravity is doing work on them. And over a certain distance from when they first jump to where they get to the apex of their jump, gravity's acted on the jumper to decelerate them from 2.1 meters per second to 0. Now, because of the symmetry, when they start to fall back down, it's still gravity, and gravity's acting over that same distance. So for the same distance for gravity to take someone at 2.10 up and decelerate them to 0, as they start to accelerate them back down over the same distance, they're going to accelerate them back up to 2.10. So the velocity jump up is equal and opposite the velocity right when you pass the limb going back down. The magnitude's the same, it's just the direction is different, because the only thing providing a force here and therefore doing work here is gravity. So whether the person jumps straight up or straight down, you're going to get the same final velocity when they splash into the water. I hope you found these problems helpful. Again, these problems come from homework 5, and I promise you, you're going to encounter 3 problems on the next exam that are exactly like these problems that I just showed you. Hope you have a good one.